Okay, I'm going to go ahead and get started. This section is Communications Server. Many of you already would be able to describe TCPIP. We use it daily. Many of you may or may not know about SNA and VTAM, but you'll be able to describe that at the end. And if I were to say, list three major components of the communication server, you're going to be able to do that. You're also going to be able to describe what is the communication server. What do you mean? By the time you're done, you'll be able to describe a Z Enterprise OSA adapter, the OSA, list network security features available with communication server. So it turns out that in the late 70s and early 80s, TCPIP, while it kind of existed, DARPA created it, as some of you know, it really was not industrial strength. And one of the problems during that time frame was our network infrastructure across the world was analog. The network, the physical network, was built for voice, not for data. And it wasn't until later on that many of the analog circuits and the analog as a carrier went away and became digital. Well, in the late 70s and early 80s, if you were a large enterprise and you wanted a nationwide network, well, TCPIP really wasn't ready, and you had to use analog lines. Those analog lines were built for voice, and they were very, very small bandwidth amount for data. So what IBM did, they built something called the System Network Architecture that actually overcame some of the weaknesses of the analog line to build in stability and recovery. And what you could do with SNA, IBM System Network Architecture, you could have a host site, and then there was this special equipment that you could buy. And for example, an IBM large controller for communications, and then you could take many, many analog lines and trunk them together. So you could trunk a large group of them, and this device, this communication device, could actually separate them across the different analog lines and then put them back together again, all the data that would flow. So that way you could have a site talking to other sites across the country. And then what they did with SNA, a lot of the intelligence was inside of here in these controllers, and then that would talk to terminal controllers. The terminal controllers also had a little bit of intelligence talking to dumb 3270 terminals. When I say dumb 3270 terminals, you had the screen, but it wasn't, we didn't have a lot of times the PCs really weren't ready back then, and so these were truly display devices with keyboards that were talking to a little bit of intelligence in here that talked to more networking intelligence that was here. Now, I will let you know that this equipment here and here was a little bit expensive. It also took system programmers or systems people or network people to actually do the configuration in here. So there was an expense involved. But if you really want a nationwide network, this was the really only industrial strength game that there was. And the people that did SNA could do things that other companies could not. It gave them a competitive advantage. So that's what SNA was all about. So back in the 80s, TCPIP was being developed, and it was on analog lines, and it was maturing. It turns out that IBM, when they created SNA, it had an architecture to it, and it had layers. For those of you that really understand networking or taken any network certifications, you know these layers. There's actually 7 layers. And SNA was the first that really implement this. But SNA came around in the mid-70s, and so IBM architected it this way. We had a physical layer, control link, path control, transmission control, all the way up here to the transaction services. This is where the applications are running. And then TCPIP kind of has a layered approach, but then, of course, the IEEE, they had to make sure, well, we got to have a standard, and they called it the OSI, Open System Interconnect Network Model. Well, both the OSI mapped very nicely to what IBM came up with, interestingly enough, but of course they made it a little bit simpler to understand. So the TCPIP software stack and the SNA software stack kind of mapped each other. So for years you had a choice. I could have an SNA network, or I could have a TCPIP network. So what communication server is, when IBM, even before we put Unix services on there, we actually created a TCPIP address space. And so that you could have we had a TCPIP stack of software and an SNA stack of software. So SNA was actually serviced in the operating system environment by an address space called VTAM. VTAM stood for and it still does stand for Virtual Telecommunication Access Method. So VTAM was the address space up on the operating system for supporting the SNA environment. And I've already talked about TCPIP is a software stack to support a TCPIP environment. What IBM did is, right after we put on Unix System Services, we were able to do some very interesting things. We actually looked at VTAM, looked at TCPIP, and realized that VTAM I/O buffering mechanisms were far superior to the TCPIP I/O buffering mechanisms. So what they did is they took the VTAM I/O buffering techniques and mechanisms, and they said, we're going to have TCPIP use the VTAM I/O buffering. So they came up with a separate component called the Common Storage Management. Common Storage Management is controlled by VTAM, but TCPIP uses it for I/O buffering because it was superior. And what communication server is VTAM, TCPIP, and Common Storage Manager together comprised of communication server. So it's VTAM and TCPIP working together, and it's very powerful what we can do as a result. So VTAM is nothing more than a JCL procedure that you start up. IST, guess what the 3 characters are for VTAM? IST. And so you start up VTAM, you start up TCPIP, but VTAM must come up first because it creates the I/O buffering area that TCPIP is going to use. So now all that data coming and going, SNA can use it, TCPIP can use it. Now here's a physical diagram that I'm going to talk about. On the diagram that you're looking at, as I mentioned, the 3 components of communication server includes TCPIP, VTAM, and something we call the Common Storage Manager, which is a shared I/O buffering area within the processor. So on the physical processor, there's something called an open system adapter, that is a adapter that you put right inside the machine, and those adapters are very configurable that you can put different drivers in to talk to almost any communication device. You can talk to the fastest communication devices in the network. But once something comes in on the OSA, then it goes through the data link layer, and then what happens is rather interesting. Let's say, for instance, there was SNA traffic that was coming in. Excuse me, let's do it the other way. Let's say there was TCPIP traffic that was coming in. Well, it could actually come in, and it can flow this way. You could have an SNA application that you're talking to. And in fact, we are doing that with the TN3270. The TN3270 session that you have is an SNA session. The TN3270 on your desktop is actually considered an SNA logical unit. And when you log on to TSO, TSO is also considered a VTAM controlled logical unit, which is a application. So it's an SNA application. So actually there's SNA protocol going on between the TN3270 client and TSO. However, it's actually traversing a TCPIP network. So you can take the SNA protocol, put it inside of a TCPIP envelope, mail it across the TCPIP physical network, and then once you get up into the ZOS environment, communication server takes that envelope, and the envelope gets opened up, and inside of it is SNA protocol. So you can use TCPIP transport to handle SNA traffic. Here's another diagram showing that you could have an OSA card for a pure IP backbone, or you could have an OSA card for a pure SNA backbone. Is that possible to do? Yes. Do many people do that now with the dedicated SNA backbone? No. The reason they don't do it is expense. Some people might think, well, maybe that SNA protocol is not as good as TCP/IP protocol. Nope, that's not the case. The SNA protocol is really well thought out, extremely good network architecture, but it's expensive because of that the peripheral equipment that you got to hook up and maintain. Now, I can tell you SNA can be highly secure, but it's a bit expensive. So most people will use an IP network to carry the SNA traffic in an envelope. So the communication server itself on ZOS, this comes out of one of the books. Down here at the bottom, this is like the OSA cards, the data link. And these are different, think of them as different drivers that you can load and use, that the communication server can use to talk to the outside world. And so I won't get into this whole architecture here. Up here is the application layer. If ever you want to talk to VTAM, basically when you say things like DSpaceNet, DSpaceNet, display net, implies you're going to be getting information from VTAM. Also, if you want to get information about the common storage management information, you would do a DSpaceNet, and there's there's ways of getting, there's operands on there to get the common storage management I/O buffering information. Remember, the common storage management is controlled by VTAM, but TCP/IP uses it. If you want to do TCP/IP commands, DSpace TCP/IP, and then there's a bunch of operands. Now, to configure the environment actually ends up being pretty simple. You can actually display some things, and this is like VTAM. In VTAM, it's saying, well, I've got some device addresses for read, write, and data control. So this is an example of a VTAM command displaying some of the, actually it's displaying the device used for the OSA adapter. Here's an example, DNet CSM use for common storage management. Here's an example of a TCPIP command doing a netstat home. To make it all connect, it's actually syntactically pretty simple. However, if you read the IBM books, you're going to see a wealth of syntax and ways of doing things. But once you know what you want to do, implementing it from a syntax standpoint is pretty easy. So you can build some VTAM parameters, and when VTAM starts up, it has its parameters that it reads. And then when you start up TCPIP, TCPIP has parameters it reads, and there's a way for the two to talk to each other. In this case, VTAM has this port name that we arbitrarily call dev OSA1. And then in TCPIP, we say we've got this link, or we got this device, DEV OSA1, and that is associated with the VTAM parameter, and then we have a link parameter associated with this dev OSA1. If you turn around and you can display these, do an MVS command, display unit control block, who's allocated to device address 400 for a length of 3, we see 400, 401, 402, and that came right from here. One's a read channel, one's a write channel, one's a data control path channel. Now the OSA comes in different forms. The OSA adapter itself, you plug right into the mainframe, and you can hook up either Ethernet to it, or you can hook up fiber channel to it to talk to the outside world. I'm going to leave it at that. Now here's a configuration example, and this is rather a little bit old, because here's some old machines. These are actually very old machines here. But one thing I want to make a point of, you never see token ring anymore. And IBM built a LAN protocol called token ring that competed with the LAN protocol called Ethernet. Well, someone might assume that token ring was not as superior of a protocol because it no longer exists and Ethernet has kind of taken over for the LAN protocol. That couldn't be further from the truth. It turns out that token ring is a far superior protocol to Ethernet. Then you might ask, why are we using so much Ethernet then? 2 reasons. One reason is token ring, for every device on the ring, had to have a little teeny switch device. That little switch device did cost a little bit extra money. So token ring truly is a little bit more expensive than Ethernet. Well, but isn't it a better protocol? Yes. Well, Ethernet, if ever you go look at what the protocol is, it's called CSMA/CD. The CD is collision detect. So what happened was, when Ethernet was first built, you could build an Ethernet bus, and like through copper, and if 2 workstations on that LAN, if those 2 workstations were transmitting a huge amount of data between the 2 workstations, all the other workstations on that Ethernet bus would slow down to a grinding halt because of collisions, collision detect. Well, they made Ethernet so fast that they could avoid the collisions. Token ring never had collisions. It was architected differently to pass a token on a ring. So no 2 workstations could dominate the LAN bus. But Ethernet got so fast they could avoid the protocol problem, and Ethernet was very cheap. So that's why Ethernet kind of rules out there for LANs right now. So a mainframe can connect to many different things. It can connect to even the fastest switches in the network. When we talk about communications also, I want to make a comment about hyper switches and vSwitch. Essentially, think of this as inside of a mainframe, you can be running hundreds, even thousands of operating systems inside what we call the books. All these operating systems can talk to each other using the backplane of the processor, and that means the network traffic never leaves the processor between those two operating systems. The network delay using hypersockets and vSwitch is nearly zero. So one thing about server consolidation, you eliminate network delay, you eliminate cables, you eliminate having to do a lot of network management. Also, you're sharing a power source. And so communication server gets involved in communicating using the hardware of the mainframe by way of hypersockets and vSwitch. Now, it turns out that Paul was actually previously talking about RACF as part of the security server. It used to be, not any longer, that the security server included something we used to call firewall technologies. It was in the wrong place. So firewall technologies no longer exist as a product, but our communication server is loaded with all the firewall technologies and security. It's the place to have it. So communication server, highly configurable to put all kinds of security in place in addition to the RACF protecting resources. So you can do encryption. You can have your IPsec chains. You can do intrusion detection services. So there's a huge amount of security opportunities within communication server itself. Where the security layer is, if ever you did a Google search on AT-TLS, you would actually learn a lot about the security. And so these security layers are the IPsec chain is down here. This for encryption, we have some up here, and right here before the application layer. And there's a whole, you could read a lot about the security capabilities of communication server by just doing Google searches or reading some of the manuals that we'll talk about a little bit later. This goes into a little bit more of an elaborate discussion, but to understand this whole scheme here, you know a little bit more now. In terms of, see up here, SAF protection. Now you can interpret this better. You know what SAF is. SAF is a system authorization facility that comes with the base element. It's part of the operating system. And SAF can talk to whatever security manager you have in place. So if RACF's in place, it'll use RACF. If you write to the SAF interface, you could have different security packages involved with the communication server network. So I'm not going to go into great detail about this, a very function-rich area for security. As I mentioned, there's a huge number of manuals. If you go to the bookshelf, you'll find a whole bookshelf on communication server. And there's a number of books. Some say SNA, some say IP. There's socket programming books in there. Very, very function-rich what you can do with communication server on the mainframe. And, of course, communication server, because it includes TCPIP, whenever you have TCPIP, TCPIP and TCP includes standard applications like FTP, like Telnet, there's any number of TCP applications that are just part of TCP. And of course, anything that's a part of TCP is involved in communication server. One last comment I want to make about this is that this communication server package that includes both SNA and TCPIP together, it doesn't exist just on ZOS. We have made a communication server for Windows. We've made one for Linux. We've made one for ZVSE. We've made one for, so communication server runs, and it runs on AIX. So we've actually created a communication server for a lot of different platforms, meaning it's TCP/IP and SNA software stack working together, and they're tightly integrated. So that's what communication server is. So now we described TCP/IP, we described SNA and VTAM, because VTAM is the address space to support SNA. List the major components of communication server, TCP/IP, VTAM, and they've got a thing called the Common Storage Manager for the common I/O buffering of both VTAM and TCP/IP. Describe the Z Enterprise OSA. That's an open system adapter. You actually plug that adapter into the mainframe, and you can hook up cables to go to your network equipment or even other mainframes. List network security features available with communication server. Well, you can do the IPsec change, you can intrusion detection support, encryption. For example, it's very, very easy to actually encrypt the FTP server. Very easy to encrypt all traffic, data control, and data itself. Very easy to go into the FTP server parameters, turn a couple things on, everything's encrypted. But then you have to have an FTP secure, capable client to be able to participate. And there's a lot of them out there. Okay, so that's the end of communication server.